Well, it's 6:30 in the morning, and I thought I'd put this together as a quick video that just looks at biogeochemical cycles. We've been learning about ecology, and we know that the study of ecosystems involves the study of abiotic factors and the study of biotic factors. And here, when we talk about the abiotic, we typically are referring to those things that are not living but interact with the living world. And these things typically are molecules, weather, and substrate. So substrate's a reference to soil and altitude and things of that nature. And biotic refers to that sum of interactions that I often refer to as plus-plus interactions, where two organisms interact with each other and they have a positive benefit to each. A plus-minus interaction where we have one winner and one loser. A minus-minus interaction where both interact and lose, and often we have a plus-zero interaction where we have a winner and one that doesn't have an impact at all. Regardless, the study of ecology involves these biotic factors because biotic factors have a direct impact on the biotic life and the type of biotic interactions. So what I'd like to do is I'd like to spend a little bit of time discussing one type of biotic interaction or biotic character, and those are the things that we refer to as the biogeochemical cycles. And bio means life, and geo is a reference to the earth, and of course chemicals is a reference to chemicals, and this idea is that there are certain chemicals that are constantly being cycled or recycled in the Earth's ecosystem or collective ecosystem that we call the biosphere. And the chemicals that I'm referring to are things like water, and we talk about a water cycle, phosphorus, and there is indeed a phosphorus cycle that allows phosphorus to be incorporated in life and then move back into the non-living world. Nitrogen, which is vital to making proteins, and nitrogen is often a limiting factor for plants. Plants need nitrogen in order to grow. Carbon, which is the base of life. It's the key element that living things are constructed from. And oxygen. And it turns out that oxygen and carbon tend to have a harmonious relationship in the process of respiration and photosynthesis. So what I'm going to do with you today really is focus on the carbon cycle, and I'll begin by talking about this harmonious relationship between carbon dioxide and oxygen, and then move directly into carbon specifically. So let's take a look at this picture here. What I've constructed for us is a pot, and that pot will have a plant growing on it, or in it. And that plant is doing photosynthesis, and in doing photosynthesis, it's going to take up carbon dioxide from the environment. This would be in the atmosphere. It's going to take up water, because we are good horticulturalists, so we're going to water our plants. And as a result of taking these two things in, that is CO2 plus H2O, it's going to make its tissues. And its tissues are made out of the molecule C6H12O6. And that molecule will be polymerized, and this molecule is glucose. And if we polymerize it, we end up making starch, which for life, this combination tends to be food. Now, a negative byproduct of doing this process, that is, doing photosynthesis, is the release of oxygen. And so this is waste. And I'll also put the glucose as a reactant. Note this equation is not balanced, but what you are seeing here is the photosynthetic equation. Now, and let me put an arrow in for the release of oxygen here. Now, one of the things that many of us don't normally think about is that plants actually will consume their own glucose. So sometimes plants, well, all the time, plants will actually take their glucose in, use their oxygen, and then release carbon dioxide and water. Typically, we talk about animals doing this, and that process is respiration. So let's create an animal here. And so this animal will be a part of our small ecosystem. And that animal is a mouse, hopefully you can tell. And what it's going to do is it actually exhales CO2. It inhales oxygen. It consumes glucose, seeds, starch, and it releases water. And so the process that I just described here, in which oxygen plus glucose produces CO2 and water, is called respiration. And this is done to get cellular energy called ATP. And if you have a mitochondria, those with mitochondria, well, you do respiration. So I would just like you to take a quick look at this and notice how carbon is being transferred from the plant to the animal, and then the animal is re-releasing the carbon in the form of carbon dioxide. We can also see how oxygen is being transferred from the plant to the animal, and that the animal is releasing some of that oxygen in the form of water. And you can note that the equation for photosynthesis is the opposite of the equation for respiration. So this is the cycling of carbon dioxide. And now let's just look at carbon more properly. And this is a summary of what is happening with carbon in an ecosystem. So what I'd like to do is I'm just going to take you through this picture, and I'm going to begin with carbon dioxide entering the plant. Now, that plant is going to use that carbon dioxide, and it's going to make glucose. And that glucose is going to be food for our pig or anything that's going to eat that plant. And as a result, the carbon that was in that food, which I'm going to represent as red, has been transferred into the pig or the cow or whatever the consumer is. And in that transfer of carbon, some of its use of the food is going to cause the re-release of carbon dioxide. Now, plants eat their own tissues. And when they eat their own tissues, in order to make ATP, they too will release carbon dioxide. So when plants are doing photosynthesis, they use carbon dioxide. But when they're doing respiration, they release carbon dioxide. Similarly, when a human consumes a cow or a pig, the carbon in the proteins and the carbs and the lipids that are in that animal get transferred into the human. And they too will do respiration in order to make ATP so that they can live. And as a result, they're going to exhale CO2, and all of this becomes part of what we call atmospheric CO2. And this atmospheric CO2 is typically re-gobbled up by plants doing photosynthesis. Now, sadly, we do not live forever. And so when things die, they decompose, and sometimes we have decomposers that are now going to consume the dead carbon. So again, I'm going to use red to represent carbon being transferred into the decomposers. But the decomposers will also do respiration. And when they do respiration, that carbon will be released as CO2 and contribute back to atmospheric CO2. Now, not everything decomposes. A lot of stuff gets buried. And if it gets buried for a long time, then that buried stuff becomes fossilized. And if we look at this over the course of millions of years, that fossilized stuff becomes fuel. But this fuel is all carbon-based. It's carbon-based because life is carbon-based. So when a plant gets buried, its carbon gets buried. And when an animal gets buried, its carbon gets buried. And when a human gets buried, its carbon gets buried. And carbon is energy. That's how come we can make ATP with it. And that energy is the same energy that we harvest in our fossil fuels. And so the pump here is illustrating oil, which is carbon-based. And it serves as the primary fuel for modern life, that is, combustion. And every time we burn something that is derived from some of this fossil fuel, then we are going to contribute more CO2 into the atmosphere. And so this oil pump pulling oil from the ground is pulling oil from what we call a sink. We call it a sink because we have sunk the excess carbon underground. And oil, natural gas, and coal, and peat all form what we call carbon sink. To close this up, we are seeing an increase in atmospheric carbon that appears to be linked to industrialization. And that increase in atmospheric carbon is having a profound impact on weather patterns and global climate. Well, that's it. That's the carbon cycle. I hope this helped. Have a great day.